In this presentation, air conditioning experiment, which is the first experiment of the machine laboratory, is going to be examined. The purpose of this experiment is to introduce air conditioning units and to understand basic processes such as heating, cooling, humidification and dehumidification in this device. Also, it is aimed to determine the properties of atmospheric air using psychometric chart and reading psychometric chart. Human beings have an inherent weakness. They want to feel comfortable. They want to live in an environment that is neither hot nor cold, neither humid nor dry. Nobody wants to live or work in a kind of place which is too hot or too cold. However, comfort does not come easily, since the desires of the human body and the weather usually are not quite compatible. Achieving comfort requires a constant struggle against the factors that cause discomfort, such as high or low temperatures and high or low humidity. It did not take long for people to realize that they could not change the weather in an area. All they can do is change it in a confined space, such as a house or a workplace. In the past, this was partially accomplished by fire and simple indoor heating systems. Today, modern air conditioning systems can heat, cool, humidify, dehumidify, clean and even deodorize the air, in other words, condition the air the people's desires. Air conditioning systems are designed to satisfy the needs of the human body. Therefore, it is essential that we understand the thermodynamic aspects of the body. The human body can be viewed as a heat engine whose energy input is food. As with any other heat engine, the human body generates waste heat that must be rejected to the environment if the body is to continue operating. The rate of heat generation depends on the level of the activity. Heat transfer is proportional to the temperature difference. Therefore, in cold environments, a body loses more heat than it normally generates, which results in a feeling of discomfort. The body tries to minimize the energy deficit by cutting down the blood circulation near the skin. In hot environments, we have the opposite problem. We do not seem to be dissipating enough heat from our bodies, and we feel as if we are going to burst. We dress lightly to make it easier for heat to get away from our bodies, and we reduce the level of activity to minimize the rate of waste heat generation in the body. We also turn on the fan to continuously replace the warmer air layer that forms around our bodies as a result of body heat with the cooler air in other parts of the room. Air conditioning systems can be classified according to their applications as comfort air conditioning systems and process air conditioning systems. Comfort air conditioning systems provide occupants with comfortable and healthy indoor environments in which to carry out their activities. Process air conditioning systems provide needed indoor environmental comfort control for manufacturing, product storage, or other research and development processes. Air conditioning processes include simple heating, raising the temperature, simple cooling, lowering the temperature, humidifying, adding moisture, and dehumidifying, which means removing moisture. Sometimes two or more of these processes are needed to bring the air to a desired temperature and humidity level. Air is a mixture of nitrogen, oxygen, and small amounts of some other gases. Air in the atmosphere normally contains some water vapor or moisture and is referred to as atmospheric air. By contrast, air that contains no water vapor is called dry air. It is often convenient to treat air as a mixture of water vapor and dry air, since the composition of dry air remains relatively constant, but the amount of water vapor changes as a result of condensation and evaporation from oceans, lakes, rivers, showers, and even the human body. Although the amount of water vapor in the air is small, it plays a major role in human comfort. Therefore, it is an important consideration in air conditioning applications. For air conditioning applications, dry air can be treated as an ideal gas with a constant Cp value of 1.005 kJ per kilogram Kelvin. Taking 0 degrees Celsius as a reference point, the enthalpy and enthalpy change of dry air can be determined from this formula that is on the right hand side. Since the partial pressure of water vapor is very low, it would be very convenient to also treat the water vapor in the air as an ideal gas with negligible error, which is 0.2%, under 0.2%, even when it is a saturated vapor. Therefore, water vapor in air behaves as if it existed alone and obeys the ideal gas relation. Then the atmospheric air can be treated as an ideal gas mixture whose pressure is the sum of the partial pressure of dry air and that of water vapor with this formula. Moreover, since water vapor is an ideal gas, the enthalpy of water vapor is a function of temperature only. Therefore, the enthalpy of water vapor in air can be taken to be equal to the enthalpy of saturated vapor at the same temperature. The amount of water vapor in the air can be specified in various ways. One of the most logical ways is to specify directly the mass of water vapor present in a unit mass of dry air. This is called absolute or specific humidity, also called humidity ratio, and is denoted by omega and can be found with this formula. The unit of specific humidity is kilogram water vapor per kilogram dry air. It can also be expressed in terms of partial pressures with the second formula. 0.622 comes from the ideal gas equation with R constant. In other definition, relative humidity, which is the ratio of amount of moisture the air holds to the maximum amount of moisture the air can hold at the same temperature, it is denoted by phi. Specific, the relative humidity ranges from 0 for dry air to 1 for saturated air. Absolute humidity and relative humidity can be related with the following equations. Atmospheric air is a mixture of dry air and water vapor, and thus the enthalpy of air is expressed in terms of the enthalpies of dry air and the water vapor. In most practical applications, the amount of dry air in the air-water vapor mixture remains constant, but the amount of water vapor changes. Therefore, the enthalpy of atmospheric air is expressed per unit mass of dry air instead of per unit mass of the air-water vapor mixture. The total enthalpy, an extensive property of atmospheric air, is the sum of the enthalpies of dry air and the water vapor, and the last equation can be found dividing by m sum a. The ordinary temperature of the atmospheric air is frequently referred to as the dry bulk temperature. The dew point temperature is defined as the temperature at which condensation begins when the air is cooled at constant pressure. In other words, it is the saturation temperature of water corresponding to the vapor pressure. The process is given in figure 2.1.1. As the air cools at constant pressure, the vapor pressure PV remains constant. Therefore, the vapor in the air, state 1, undergoes a constant pressure cooling process until it strikes the saturated vapor line, state 2. The temperature at this point is TdP, and if the temperature drops any further, some vapor condenses out. The air remains saturated during the condensation process and thus follows a path of 100% relative humidity, the saturated vapor line. The ordinary temperature and the dew point temperature of saturated air are identical. Relative humidity and specific humidity are frequently used in engineering and atmospheric sciences, and it is desirable to relate them to easily measurable quantities such as temperature and pressure. One way of determining the relative humidity is to determine the dew point temperature of air, which is discussed above. A more practical approach is to use a thermometer whose bulb is covered with a cotton wick saturated with water and to blow air over the wick as shown in figure. The temperature measured in this manner is called the wet bulb temperature, and it is commonly used in air conditioning applications. The wet bulb temperature can also be measured by placing the wet wick thermometer in a holder attached to a handle and rotating the holder rapidly, that is, by moving the thermometer instead of the air. A device that works on this principle is called a sling psychrometer. The state of the atmospheric air at a specified pressure is completely specified by two independent intensive properties. The rest of the properties can be calculated easily from the previous relations. The sizing of a typical air conditioning system involves numerous such calculations. Therefore, there is clear motivation to computerize calculations or to do these calculations once and to present the data in the form of easily readable charts. Such charts are called psychometric charts, and they are used extensively in air conditioning applications. The basic features of the psychometric chart are illustrated in this figure. The dry bulb temperature are shown on horizontal axis, and the specific humidity is shown on the vertical axis. On the left end of the chart, there is a curve called the saturation line instead of a straight line. All the saturated air states are located on this curve. Therefore, it is also the curve of 100% relative humidity. Other constant relative humidity curves have the same general shape. Psychometric chart for a pressure of 1 atm is given at the end of the document. Psychometric chart at other pressure for use at considerably higher elevations than sea level are also available in the literature. Let's watch how the psychometric chart is read.
Psychometric chart. Psychometric chart is a graphical representation of the physical and thermodynamic properties of air. Whenever you are going to do air conditioning, then you have to change the properties of air. And if you want to change the properties of air, then you must need to know how to measure the properties of air. So psychometric chart is used to measure the properties of air. Following parameters are seems to be plotted on this chart. Number 1, dry bulb temperature, wet bulb temperature, relative humidity, absolute humidity or humidity ratio, dew point temperature, specific volume, enthalpy. We will learn all these parameters one by one and plot it on psychometric chart. This is psychometric chart, and I am not going to discuss it right now because it seems to be very complex. Let's make it simplest stepwise. First of all, we will discuss dry bulb temperature. It is the normal temperature of air, or it can be measured simply by a normal thermometer. For better understanding of psychometric chart, 2 points should be kept in mind. Number 1, you need to identify the line, that which line represents which parameter and where is the scale of parameter. If you know these two, if you keep in mind these 2 points, then this chart will be very easy for you. Suppose this is psychometric chart. Let's draw dry bulb temperatures on this chart. This is the scale on horizontal axis or x-axis for dry bulb temperature, and it increases from left to right. So we'll find out the scale of the parameter, which is on horizontal axis. Now let's draw the lines of dry bulb temperature. These are the lines of dry bulb temperature on psychometric chart. I think dry bulb temperature is clear right now. Let's move to the next parameter. Wet bulb temperature. This is the temperature which is measured by wrapping a wet cloth on thermometer. We have already made a video on this topic. Let's find out its line position and its measuring scale on psychometric chart. This was the scale of dry bulb temperature. These are the lines of wet bulb temperature, and here is its scale. So wet bulb temperature lines are as seems to be inclined line around at the angle of 25 to 30 degree. These lines shows the wet bulb temperature line, and this scale shows wet bulb measurement scale. Let's move to the next parameter, humidity ratio or absolute humidity. For example, if you have a 1 gram of air, then how much water is present in 1 gram of air in grams is humidity ratio. Since in 1 gram of air, the water quantity or water vapors quantity is very much less, so vapors is also measured in grain, which is the smallest unit of water vapors quantity. 1 grain is equal to 0.065 grams. When you have anything in smallest quantity, then it is better to measure it on smallest scale. Let's draw it on psychometric chart. Humidity ratio scale is on the y-axis, on vertical axis. Now let's draw its lines. Its lines are horizontal towards the wet bulb temperature line. So I think this parameter is also clear. Let's move to the next parameter. Relative humidity. Relative humidity is the amount of water vapors in form of percentage. So this is psychometric chart, and these are the relative humidity lines, and here is its scale. I think this parameter is also clear. Next, move to the next parameter. And guys, one point need to notice that this is the saturation line where the humidity is 100%. That means air is fully saturated, air is full of water vapors, and there is no more possibility for absorption of more water vapors. Dew point temperature. It is temperature of saturated air. What is saturated air? For example, this is air, and when it becomes full of water vapors, then it is called saturated air. So the temperature of saturated air is called dew point temperature. This is the scale of wet bulb temperature, and it is also used for dew point temperature scale, because this scale is drawn on saturation line, as you can see that, where the humidity is 100%. So this wet bulb temperature line and saturated line is used to measure the dew point temperature. Specifically, the dew point temperature lines seems not to be plotted on the psychometric chart. But how can you find the dew point temperature? It's very simple. Let's suppose this is dry bulb temperature scale, this is humidity ratio scale. If these two parameters you have known, then you can easily find out dew point temperature. For example, you have dry bulb temperature 28 degrees centigrade, humidity ratio 0.013. Then at the point of intersection, you draw a horizontal line towards the wet bulb temperature line in order to find the dew point temperature. I hope this is clear. Let's move to the next parameter, specific volume and also enthalpy. Specific volume and enthalpy we will discuss in single slide. Specific volume, it is the amount of it is the volume of air in per unit gram of air. Its unit is meter cube per gram, or in other words, you can say that if you have 1 gram of air, then what is the volume of 1 gram of air is specific volume. And what is the enthalpy? If you have 1 gram of air, then how much heat is present in 1 gram of air is enthalpy. Its unit is joule per gram. Now let's draw these two parameters on psychometric chart. Guys, this is wet bulb temperature lines. Why I have drawn it again? Because the enthalpy lines are very much similar to wet bulb temperature line, but these lines are extended towards the enthalpy scale. Enthalpy scale is joule per gram. Now draw the specific volume lines and specific volume scale. Its scale is 0.80 to 0.95 meter cube per gram. Now I think guys, we have drawn individually all parameters. I think it's time to draw a complete psychometric chart. Suppose this is the psychometric chart. First we have drawn the scale of dry bulb temperature, then scale of humidity ratio, then scale of enthalpy, then scale of wet bulb temperature, saturation line, dew point temperature scale. Now draw the dry bulb lines. Now draw the wet bulb lines. Now draw the humidity ratio lines. Now draw the relative humidity lines. And now draw the enthalpy lines. Now draw the specific volume lines. This is the scale of specific volume and this is the scale of relative humidity. So this was that complex chart which we didn't discuss in earlier. I hope I tried to make it very clear to you. So it's time to solve a practical example that how we can calculate required parameters on psychometric chart. For calculation of parameters, I think we move to professional chart. So in order to get the correct values, in order to use psychometric chart, you must have two parameters. If you have two parameters, then by the intersection of that two parameters, you can find out all other parameters. How, for example, your dry bulb temperature is 30 degrees centigrade, your wet bulb temperature is 25 degrees centigrade, and you need to find relative humidity, specific humidity, dew point temperature, specific volume, enthalpy. So what you have to do, first you need to draw your first given parameter and then second given parameter. Once again, dry bulb temperature is 30 degrees centigrade. So I draw the line on 30 degrees centigrade parallel to the line of dry bulb temperature. Remember one thing, whatever parameters you drawn, it should be parallel to that parameter. For example, wet bulb temperature 25 degrees centigrade, and these are the lines of wet bulb. So my point is also on 25, so my line will be parallel to that 25 line. So then we find the point of intersection. This is my point of intersection. Now guys, what you have to do, you have to draw a line from the point of intersection to the point of required parameter scale, but your line should be parallel to the required parameter scale. Repeat once again, whenever you want to find out a parameter on psychometric chart, you need to draw a line parallel to the required parameter line till the scale of required parameter. For example, relative humidity, my intersection point is between 60% humidity line and 70% humidity line. If I draw a line parallel to these lines, then it will be nearest to 70% line. So my relative humidity is around 68%. Specific humidity or relative humidity, my specific humidity lines are horizontal. So when I draw a horizontal line parallel to these lines to the scale of humidity ratio, so I can get specific humidity. My specific humidity point is between 0.015 and 0.020, but it is nearest to 0.020, so my value is 0.018. For dew point temperature line, as we have already discussed, from point of intersection horizontal to the wet bulb temperature, so my dew point temperature is between 20 and 25 and it's around 23.5. For specific volume, my specific volume lines, where is my specific volume lines? This is my specific volume lines, 0.80, 0.85 and 0.95. So I draw a line parallel to these two lines, then it is find that my specific humidity line is between 0.85 to 0.90, but nearest to the 0.90, So my specific volume is around 0.88 meter cube per gram. Let's draw enthalpy. From point of intersection, I will draw a parallel line to enthalpy lines towards a scale. Then my line is between 60 to 80, but very nearest to 80. So my enthalpy is around 75 joule per gram.
This is the psychometric chart. Let's continue. There are four main air conditioning processes: heating, cooling, humidification, dehumidification. Combinations of these four are frequently applied during the air conditioning processes. Various air conditioning processes are illustrated on the psychometric chart in this figure. Notice that simple heating and cooling processes appear as horizontal lines on this chart, since the moisture content of the air remains constant during these processes. Air is commonly heated and humidified in winter and cooled and dehumidified in summer. Notice how these processes appear on the psychometric chart. Elements of the experiment setup can be seen in this figure: control board, low pressure manometer, emergency button, main switch, radial fan, preheater, condenser, compressor, filter dryer, sensors, cooler, humidifier, afterheater, and outlet section. Okay. Let's make experiment of air conditioning. First of all, we make sure of the electrical connection. Then we open the leakage current relay and the fuse. After that, we turn on the main switch and the control panel turns on. There are four menus in the control panel: settings, measurements, first and second control menus. We are not concerned with the options in the settings and measure menus. The part that interests us here is the first and second control menus. In the first control menu, we can switch on and switch off the radial fan, preheater, afterheater, cooler and humidification sections. Also, we can change the level of fan speed, preheater and afterheater. In the next page, the related values, which are temperature, relative humidity and velocity, can be read with the aid of sensors. These are the sensors in specific sections, you can see. And the last section, there are two sensors. One of them is velocity and the other one temperature and relative humidity sensor. In the last page of the screen, power value of cooler. In the last bit, power value of cooler or refrigeration groups, preheater and afterheater can be read. And second control menu gives us a general schematic view of the air conditioning setup: radial fan, preheater, cooler, humidifier, afterheater, exit or outlet, and refrigeration cycle or refrigeration groups. You can see all values in one page. In this experiment, two seasons can be observed: summer season and winter season. Let's start with summer season. For summer season, radial fan, cooler and afterheater should be switched on. Cooler one should be levelized to the higher level, because we want to cool air. We want cool air. The radial fan must be always open for winter and summer season, since it simulates the outside air. Cooler should be open because of the hot weather in summer, and finally after heater also be open, because the cooler cools air up to undesired level, but we want to ideal level temperature in living or working place. After heater provides the desired temperature level, and humidifier shouldn't be open since weather is humid enough in summer season. Radial fan is switched on and it starts to operate. The sensor that is very next to the fan gives us temperature and relative humidity of the outside conditions. The air firstly reaches preheater, but preheater is not open, so temperature does not change. After cooler is opened, the temperature of air drops when reach the cooler. These are the refrigeration groups with compressor, condenser, filter and evaporator or cooler. This one, the cooler. These are the refrigeration group. In this section, the humidifier can be seen, but it is closed. The air continues to move to the after heater after leaving the cooler. With switching on after heater, the air reaches the desired level temperature which we want, and after passing the after heater, the air leaves the setup from these channels. If we check the second page of the digital screen, T1, T3 and T5 change, and also relative humidity value of section 1, 3 and 5 change. T2 and T4 do not change because preheater and humidifier do not operate. You can see temperature values and relative humidity and finally velocity. And in the last page of the screen, only refrigeration and after heater power values can be read since they operate in summer season. Only cooler and after heater. This is the end of the summer season. All components are closed to start winter season. You can see the fan is slowing down. For the winter season, the radial fan level is decreased to simulate outside air. Preheater must be opened and its level should be arranged with the same way after heater should be levelized at a specified level. For winter season, radial fan, preheater, after heater and humidifier should be switched on. Humidifier must be opened since the weather is very dry in winter season and we do not want to dry air in our living or working places for our health. Only cooler should be held closed. Again, the air moves to the preheater. After leaving the fan, the temperature of the air increases leaving the preheater, and after leaving the preheater, the temperature of air is increasing and it reaches the cooler, but cooler is closed and temperature and relative humidity does not change. The air reaches directly to the humidifier. You can see the drops of water. They fall in the humidifier. While hot air passes the humidifier, the water drops catch some of the hot air and air gains some water drops. Thus, the air turns to the humid air. After leaving the humidifier, it reaches the after heater and subliming a little bit, and then the air after heater leaves the setup from the these outlet or exit channels. This is the schematic view of experiment. Preheater is opened cooler is not opened, humidifier opened, and after heater is opened. In the next page, the temperature and relative humidity values and power values can be read from the screen, like a first experiment, which is the summer season. T1, T2, T3, T4, T5, all temperature values can be read from this panel, but cooler is not opened for winter season, and preheater and afterheater have values because they are opened. When finishing the winter season, all components and switches are closed. Main switch are closed. And relay and the fuse are closed, and electrical connection is closed. This is the end of the air conditioning experiment. All the necessary parameters will be given to you to the calculations in the experiment. Please read the laboratory manual carefully. All formulas you need are in this paper. Be careful with the units while doing calculations. Thank you for your time listening and watching this experiment.